Okay, good morning, everybody, and thank you for inviting me. When Roberto first contacted me, he asked me, do you want to discuss about the interplay between FCC-ee and FCC-hh? And I said, I would like to. Thank you for inviting me to this nice conference. The problem, of course, is that the complementarity is so strong that it means that I should cover both FCC-ee and FCC-hh programs, which is a huge thing. I mean, as you will see, I will just focus on Qcd and Higgs, given the topic of the workshop. But you will see that every single topic can give for a talk. So I'll try to address some of the things that we can do with such an amazing machine. So first of all, why building a new collider? And let me just repeat the usual motivation, not just because we all not know, but because it's important to emphasize all those topics so that we interiorize them in order to convince our fellow physicists and then eventually the politicians, the public, for the need to spend money over the next 30, 40 years in building a huge collider of 100 kilometers. So it's important that we all know why we want to do it. And if you just want to say it in one simple word, is that the reasons by which we build the LHC are all there, except for the Higgs that we discovered it, but now we want to study it in more detail. But the rest of open problems that we are facing in particle physics are there. So the LHC so far, unfortunately, has not solved all the things that I will mention now. First of all, let's take a look at the standard model Lagrangian, and that describes nature, forces and particles, as we know. The first thing we have to say is that the usual claim that the Higgs mechanism of mass generation of the standard model particles has been proven with the Higgs discovery is not true. The lightest fermions that form actually a stable matter in the universe, light quarks, electrons, let alone neutrinos, the particles that make this 5% of the visible universe, that we don't know. We didn't check that they get their mass through the Yukawa coupling to the Higgs field. So this is something that we need to test. Maybe there is some new dynamics going on, and actually, so far we know how the WZ and top and third family get their masses, but not the visible particles of the universe. Then, of course, there is the big issue of the neutrinos. This goes into a big second big problem, which is the flavor problem. It's not just the matter-antimatter asymmetry, but it's understanding how the fermion pattern of masses and mixings exists. So far, it's just a given. We don't know. We'd like to understand why there is this large span of Yukawa couplings, if you want. Eventually, the particles will get their mass to the Higgs. So from the neutrinos, if they are Dirac, all the way up to the top, and all the way the particle mix in flavor and Qcd states, all this is a complete unknown today. And this has not been solved by the LHC. Then there is the Higgs sector is not yet fully studied. We need to understand how the Higgs potential, how the Higgs couples to itself. In a way, I like to say it, how the Higgs mass, so how the Higgs field gives mass to itself. And this is something that for this we cannot just study at the LHC, we don't have the energy. Then there is, of course, the problem of fine-tuning, hierarchy, the fact that the Higgs mass is unprotected up to the Planck scale, that is a theoretical problem. Then the big elephant in the room, dark matter describes only 4 or 5% of the universe. And in principle, the Higgs should couple to this dark wall, and this we have to study. Plus many others, as a strong CP problem, actions, dark energy, inflation, quantum gravity. All these issues here, I see 6, 7, 8, I don't know, you name it. We have 9, 10 fundamental problems in particle physics that are unsolved. And for this, we need to go beyond the LHC. So the next machine that we can build is a machine with the current technology, or the technology will be available in the next 20 years for the magnets. It's a 100 kilometer type of machine with niobium tin 16 Tesla magnets that will give us 100 PV machine, basically roughly an order of magnitude increase in center of mass energy, and also an order of magnitude increase in integrated luminosities. 2 inverse atobans per year, you integrate over 10, 20, 15 years, you get 30 inverse atoban, whereas the LHC will give you 3 inverse atoban. And before this, of course, the priority of the particle physics community is to build a Higgs factory to really probe this new scalar boson with high accuracy. And for this, we need E plus, E minus, which are very clean and allow you to probe the couplings to the standard model particles to high accuracy. And then this machine gives you also a huge luminosity Higgs factory with 1.2 million Higgs plus you will see 10 to the 12 Z's, 10 to the 11 W's, million tops, and so on. So the mandate we're following here, the mandate of the European Strategy for Particle Physics update of last year that told us to investigate the technical and financial feasibility of a future hadron collider, starting up with at 100 TeV, starting up with electron-positron Higgs and electroweak factory. And we need to provide these feasibility studies before the next strategy update in 5 years, 2025, 26. So the project again is a stage 1. So the goal is stage 1 is to have an E plus, E minus Higgs factory. Well, actually Higgs electroweak and top factory with the highest possible luminosities, exploring the heaviest particles of the standard model, W, C, Higgs, and top, followed by an operation of 100 TeV PP. The time the 15 years where we run the FCC-ee, we have the time to develop all the magnets for this for the hadron collider. So here we have the combination of ultra precise standard model tests, indirect VSM reach with respect to direct discovery searches at high masses. So the two machines give you that you will see a huge lever arm compared to today. Of course, why at CERN? Because at CERN it's an existing lab with an existing infrastructure with thousands of people that know how to build colliders and run colliders for 50, 60 years now. So of course, then you have a common tunnel, common civil engineer, technical infrastructures. And then in principle, if the high Lumi LHC will end up at 2030, 36, and the FCC could start in 2040, so it's a almost continuous operation of collider physics in the world. Of course, there are competing alternative machines, linear machines in particular for the Higgs factory. You will see the importance of circular is not that much. Of course, that the advantage of linear is that you can upgrade them to few TeV elementary collisions. The advantage of circular is that you can have huge luminosities that basically give you negligible statistical uncertainties for a standard model Higgs Qcd electroweak flavor studies, and thereby indirect VSM studies up to 50 TeV. You will see it later on. So this is the idea. Right now we are here, feasibility study in the next 5 years. Then if this gets approved, then we construct the tunnel, we install the detector, and then when high Lumi LHC ends up, we start around 2040 with the FCC-ee, about 15 years operation, followed by then the FCC-hh. Given the title of the workshop, I will focus mostly on QCD, and you will see that, of course, one thing that for QCD studies, you need a PP machine. I will try to show you that it's actually plus E minus the best thing to do, as you will see in terms of precision QCD for alpha edge coupling, not for PDFs, but just for jet substructure, flavor tagging, and also for the non-perturbative regime. And then I will go to Higgs, and then we'll end up with VSM searches. So QCD is a key piece at future E plus, E minus, and PP colliders. This is not per se, of course, the main driving force behind these machines, but it's crucial for many PP and EE measurements for both signal and backgrounds. So if the first thing, I will devote some time to this, we need alpha S with per mil uncertainty to be able to compute cross sections and decays involving jets. So and to the same to per mil accuracy. This is true for the Higgs, for the top. If you want to determine a top mass for electroweak precision observables, we need alpha S with per mil. So at least 10 times better than today in order to really exploit any BSM searches at any other, at any PP machine. Then, of course, we need higher order, fixed order corrections and log resumations. If you want to compute any perturbative cross sections and decays with high accuracy, we need high precision PDFs at FCC-PP in order to look for to do precision tests of the standard model at the WZH range, as well as all searches at high X. In PP collisions, we need to know well the gluon at high X and so on. We need to have heavy quark, light quark and gluon separation with very high accuracy for any precision SM, as well as BSM searches with final jets. I will discuss this a bit. Then we have to control semi-hard QCD, low X gluon saturation, multiple hard partner interactions. Note that the FCC-PP, the typical scale at which all these semi-hard dynamics sets in is 10 GeV. So it's not anymore a low scale. I mean, at 10 GeV, we will have multiple hard partner interactions. We will have maybe already gluon saturation leaking in, and so on and so forth. And last but not least, non-perturbative QCD FETs, color reconnection, hadronization, final state interactions. All these impacts final states with jets, even in E plus, E minus, going to 4 jets, 6 jets, going to WWZ, TT bar, and so on and so forth. And this impacts MW, top extractions, you will see that. So let me try to convince you that that E plus, E minus is an amazing tool to study QCD. And you already see it here. Compared to PP collisions, you have a QED initial state with non-kinematics. You know perfectly what is the center of mass energy of your interaction, not like the PP where you probe PDFs over many orders of magnitude. You have controlled QCD radiation. You only have final state QCD radiation, nothing like ISR, gluons. You have well-defined heavy quark and gluon jets. I mean, if you go to any jet substructure talk at the LHC, and you've been hearing for many years that there is no way to define a gluon jet, and that's not true. You just go to E plus, E minus at the Higgs Strahlung, and you look for Higgs to glue, and that's actually much more dominant than any Higgs to light quarks. And the other way around, you go to the Z, and then the Z can only decay to quarks, not to gluons. So the distinction between quark and gluons is perfect in an E plus, E minus. It's not the case in a PP because basically flavors rotate, and the initial state is unknown. The initial part on flavor is unknown. Of course, you have much smaller non-perturbative uncertainties. You start without PDFs already, partonic PDFs. You don't have any underlying event. And then you have a direct access basically to the final state parton fragmentation and hadronization. And then you also have gamma to QQ bar and vector mesons in photon-photon collisions. So that's also that gives you some insight into different phase spaces of QCD. So let me show you again these numbers. This is the working points, the Z-pole, WW, Higgs Strahlung, TT bar, and maybe S-channel Higgs. I will mention that in my Higgs part. And you realize immediately the huge amount of QCD jets that you will produce. So at the Z-pole, you are dealing with 10 to the 12 Higgs, 10 to the 11 gluons. If you let go for 3 more Mercedes-Benz type of topology, you know that one of the third jet is a gluon. And of course, most of them are heavy quarks. In the case of the Z, you have the numbers for the W, the Z. In the S-channel Higgs, if you run 125, also the backgrounds are produced, all the same processes that produce quarks for at the Z-pole produce quarks in the continuum, also Z star, gamma star. And then, of course, you have, in particular, in the case of the Higgs Strahlung, you have 200,000, 100,000, 120,000 actually pure Higgs to glue. That's an amazing thing to calibrate our models, our calculations for gluon radiation fragmentation. So let me go rapidly through the QCD topics. Alpha S coupling. Just remind you what the status is. I mean, you know that the QCD coupling is the single parameter of the QCD. QCD is a theory that has a single scale in the chiral limit where you forget about quark masses. You only have one coupling, and that defines the full theory. You know how the coupling runs, and we usually define a point to measure it at the Z pole. And you see how the uncertainty has been going on in the last 30 years from 6, 2.5, 6 per mil a few years ago. Today, we are at about 1 per mil, 1%. Because there are some, when you add more data, there are some results that are not fully consistent, and then the uncertainty the precision has decreased, has decreased, the uncertainties have increased. So the first motivation, what to measure alpha S, well, it is the least precisely known of all interaction couplings. I mean, not just the QED or the Fermi coupling is also the gravitational coupling is much well known than the alpha S today. Is much better known. So that's a weird situation. But it's not just this generic motivation, is that, as I said, alpha S impacts all QCD cross-sections and decays for Higgs and all precision standard model studies. If you want to measure the top mass, for example, at T plus minus through a threshold scan to TT bar, you need to know alpha S. Otherwise, you will never get to the MEV precision that you expect. You have already theoretical uncertainty is much larger than the experimental one. If you want to look at electroweak precision observables like the width of the Z or the ratio of different decays of the Z, today the leading uncertainty is parametric in the calculations. So if you want to do any stress test of a standard model, you need to know better alpha S. And of course, not only this, as I said, if you want to determine the Yukawa coupling of the Higgs to the CC bar or Higgs to glue, here the uncertainty of these partial widths today is you see 4%, 7% from alpha S. And if you want to compute it a PP bar collider gluon Higgs or TTH, again, you have here alpha S propagating today to 3-4%. So we need to reduce alpha S uncertainty, at least a factor of 10, if we want to do strong tests of the standard model. But it also impacts physics approaching the Planck scale. As you all know, you see the evolution of Higgs quartic coupling as a function of the scale. And this depends, of course, on Higgs and top masses, but also the third parameter that enters into the game is the alpha S. So depending if it is this small, this dotted line here, okay, it seems that it's small compared to the uncertainties in top mass and Higgs, but it's already a factor of 10. Whether the electroweak vacuum gets unstable today, approaching the Planck scale, we don't know within a factor of 10 because already the uncertainty is running off alpha S right now. And also if there are new galvanify theories and you want to test the unification of couplings, you need to reduce this current uncertainty from alpha S, which is the dominant one. Let's go very rapidly. So at the LHC, at the FCC-ee, we will exploit 10 to the 12 Z's, 10 to the 11 W's, and 10 to the 6 tops. Not only the huge statistical samples, it's also the fact that the line shape will be known exquisitely thanks to a very good a strong kilo electron volt knowledge of the beam energy. Basically, by resonant depolarization, we will know exactly where we're running our machine. So this allows you to determine the Z and the W masses masses and widths to within hundreds of kilo electron volts, as you will see. So it is not just that we have a huge data sample with negligible statistical uncertainties, is that the systematic uncertainty is related to the determination of the width and the mass of the two gauge bosons will be in the hundreds of kilo electron volts, thanks to this accurate knowledge of the beam energy. So let's go to alpha S. Today, if you check the PDG, it is determined through 7 observables, and you see immediately that 4 of them, or 3 of them, half of them, this will come in the future, half of them come from measurements that come from E plus E minus collisions. And you have a lattice, which is basically driven by, this is an intra QCD theoretical test complemented with hadron masses and hadron decays. Then QQ bar PDFs, this is and proton TT bar, those are hadronic observables that otherwise those here highlighted, half of them come from the plus and minus collisions. So let's take a look at tau lepton decays. This is the ratio of hadronic to leptonic decays of the tau lepton is known to N3LO with a tiny uncertainty, experimental theoretical uncertainty. The experimental one is 2 per mil, but of course you see that this is only higher order corrections. The gluon only enters into this with that as a higher order correction. So this uncertainty gets enlarged when you try to start alpha S. But currently the problem is that there are two ways to extract this R tau ratio using fixed order perturbation theory or contour improved perturbation theory, and that the different works do not exactly coincide. So this also the treatment of non-perturbative corrections. I want to emphasize here that the mass of the tau is not, it's only quotation mark 10 times above lambda QCD. So these power corrections are not small. It's a 2%, which is basically what at the end this propagates to an uncertainty today of 1.5%. So what FCC-ee will provide, if not BEL2, is much better spectral functions to really at least control the non-perturbative corrections. And of course, we will have high statistics 10 to the 11 from Z to tau tau that will bring you this, hopefully, if we solve these differences between FOPT and CIPT to the per mil level. Then we have these issues with, we have these measurements with the plus and minus event shapes and jet rates. So again, those are in principle compute to high accuracy at NLO or N3LO plus log resummation at NLL or NLL for the thrust, for the C parameter, and so on. But different parameters and different extractions today, for what you think is something which should be very clean in E plus and minus, we see that mostly how you account for hadronization correction via Monte Carlo or analytically, this propagate into a 2 to 3% uncertainty today. Of course, at the FCC-ee, we'll have many center of mass energies. We can go to even lower than 90 GeV through ISR, and this will be interesting for jet shapes. And you can go up to higher, to 350 for jet rates. And by looking into this and comparing to the theory, these uncertainties hopefully will decrease. Then the theory resummation will get improved. Soft drop techniques and some other techniques will hopefully reduce non-perturbative corrections, and this also will improve the extraction from jet shapes. So again, from this we expect per mil or below percent uncertainties. Then this is a topic I devoted myself with one student last year. It is the extraction of alpha S from hadronic Z and W decays. That's eventually the most accurate one. So this is known theoretically at N3LO accuracy with these theoretical uncertainties and parametric uncertainties that you see here. So we have three experimental seed observables, the W and Z hadronic widths, the ratio of W and Z hadronic to leptonic widths, and then also the peak hadronic cross-section. Those were measured at LEP with 1 per mil to 3 per mil for the C and 1% to 2% for the W experimental uncertainties. You see here, there have been some changes lately, small changes, very tiny, you see in those quantities, but this, as you will see, they have an impact on alpha S. Again, at the board level, all these quantities depend only on pure electroweak quantities. So any dependence on alpha S goes only through higher order. So this 1 per mil, 3 per mil uncertainty on the Z today will propagate into 2%, as you will see, and this 1 to 2% in the W propagates into 30% alpha S, as you will see later on. So this will be, as you will see next. So this will be very much reduced at the FCC-ee. So what we did, and that's the current state of the art for alpha S from hadronic C decays, what we did is we combined these three seed observables, and also we did a full standard model fit using the results from this update of the LED luminosity bias. and you see how things now look like. So the dash curves are what you find in the PDG. They are, of course, consistent all because there is a broad parabola. But when you take into account these corrections and the updated, we included also, I didn't mention this, but we included also um, electroweak corrections that have been computed, and mixed electroweak corrections for the W that have been computed lately. And you see that these, the three parabolas from the third order solvers are here, 1, 2, 3, and these now agree very, very much among them. So today we did the extraction and we get 0.1203 with a 2.3%. And with both the experimental theoretical updates that I mentioned, we have a better agreement now with a full standard model fit also. And this is better than what you find in the PDG today. The PDG today is 2.5%. We have it now to 2.3%. The central value didn't change much, but the precision improved. So at the FCC-ee now you will have 10 to the 12 Cs, and you will have this 10 to the 5 times larger statistics, and you will have also exquisite systematic and parametric precision. So thanks to this accurate knowledge of the systematic uncertainties of the center of mass energy, and so all this will propagate into an extraction of alpha S that you can see here to the 2 per mil, of which 1% is experimental, and 1 per mil is experimental, and another 1 per mil, a bit more, is the theoretical. We need to reduce the theoretical uncertainties, computing missing alpha S to the 5, and then alpha cube, and so on, and mixed corrections. But this will be a strong standard model consistency test. So imagine that the alpha S values stay at where they are for the rest of observables, and that the alpha S extract from the Z stays at where it is today. You see now that those two things are not indicate attention here. So that's the type of tests we will be able to do. The same exercise with the W today. As I said, using the W width and the RW ratio, we did a full fit combined with N3LO of calculations for these quantities. Those were not available. Okay, the calculations were available, but we put everything together. Of course, here the problem is that we have a BCS CKM parametric uncertainty that is not within 2%, that propagates into a huge uncertainty in alpha S. You see, basically it's unconstrained. Of course, the minimum is it's at 0.04 with a huge uncertainty. If you enforce CKM unitarity, then you get a much better. Okay, you get an alpha S now, which is again consistent with the world average, sitting at 0.1101 with a 27% uncertainty. Why is it so? It's because we have today W pseudo observables from Lepton from 50,000 W bosons, which basically only very mildly constrain alpha S. Of course, with 10 to the 8 W bosons, 10 to the 4 times what we collected at Lep2, we'll have, and also the exquisite systematic and parametric precision that I mentioned, also for BCS, thanks to 10 to the 12 D mesons at the Z pole, and a theoretical uncertainty reduced by a factor of 10 after computing all these higher order corrections. We expect also alpha S to be at the 2 per mil uncertainty. Okay, so you see here, we just arbitrarily put it at the world average. You see here how it compares the alpha S extraction from the W pseudo observables compared to the current world average. Now, if you put together the FCC extraction from the Z and from the W, and you see this type of discrepancy, then this is a very strong indication of a problem in the standard model. Okay, so this per mil uncertainty is only possible with a machine like FCC-ee, again looking at hadronic W and Z decays. Okay. Then of course FCC-pp will allow us to test things well beyond the TV scale, because at the end we are determining things here at 90 GeV. But we want to test the running of the coupling up to, for example, 25 TeV now, looking at the jets. So we can test asymptotic freedom and look for new color sectors above 3 TeV, for example, gluinos. If you have up to, sorry, this is TeV, this is TeV. If you have gluinos up to 8 TB, you will be able to see it in the evolution of the alpha S running, and you will see it showing up here in the jet cross-section rates with a 10% statistical uncertainty up to 25 TB. So we need FCC-ee also to test the running of the coupling up to multi-TeV energies. Let's go rapidly through the PDFs. So if there is new physics at high X, we need to control the parton densities above 0.5. And also there is an intrinsic QCD, pure QCD topic, which is what happens to the gluon at low X below 10 to the minus 4, which is basically unconstrained today. So is there the onset of nonlinear QCD evolution equations, or the GLAP still works down there? It should not work. At some point, gluons should start to recombine too. So for these, of course, these PDFs, we cannot test at the E plus A minus, but of course, we will be able to do it at the FCC-ee. Let me just tell you how we constrain PDFs today with PP data. We have 6 processes that are currently being used to place important PDF constraints: top quart and jet production. This is directly sensitive to gluons. Then, of course, the production of electroweak bosons with charm, inclusive or differential, and also the photons. All these things allow us to improve the understanding of the PDFs, mostly at high X. This is from a paper this week by NMPDF 4.0. You can see what happens now with the current state of the art in green for the U, for the S, for the charm, for the Ds, for the glue. So what happens with them if you ignore or if you include LHC data? And you see that if you don't include LHC data, you get these orange bands here, and you see changes at high X above 0.1, which are large, beyond 10 to 5%. So basically, all this data at the LHC is helping to constrain the high X species, except for the U quark. The U quark is rather well constrained by DIS. You see it here. There is no significant improvement, both in the central value and in the uncertainties. But for the rest, yes, we need a PP collider. Halloumi LHC will allow us to improve this by a factor of 2. Now, the question is whether in order to measure cross sections in the precision physics range, so looking for calculations of measurements, comparing measurements of WC and Higgs and top production cross sections to a state of the art and 3LO, whatever is the state of the art at the time of FCC-ee, we need to know, as I said, alpha S to per mil, and we need to know now PDFs also at the current 1%, much below the current 1% level. The question is whether the FCC data themselves, as we did at PP at the LHC so far, will help us to constrain this, or we need FCC-ee, okay, DIS machine. Let me go to the third topic, jet substructure. This is a topic that has exploded in the last years, basically by looking at the jet substructure through, for example, angularities, jet angularities, which are basically products of normalized energy and angular moments. And those are interesting because you can compute them, and in some cases they are even, okay, they are not infrared and collinear safe, but they are Sudakov safe in some of them. In the case of a family of them, for example, going along this line in angularities, those are infrared and collinear safe, and this can be computed with fixed order and with some calculations via SCED in the SCED framework. So this is there has been significant progress on all this. But today we have a problem is that we don't have high quality data for the gluon, and you see it, for example, the comparison of the angularities predicted for U quarks and gluons. And you see here that the U quarks agree rather well, but the gluons, they don't. And you see that the discrimination power of U versus quark exploiting this Les Souche angularity, for example, is very much Monte Carlo dependent. This is the reason being that we don't have high quality gluon data from E plus C minus collisions, that we are a clean environment. That's where FCC-ee helps because, as I said at the beginning, we have a perfectly pure sample of light quarks and gluons from the Z-pole and from the Higgs-Strahlung studies. And this will allow us to really, with 100,000 extra clean digluon events, exploiting now this channel not just to not to study Higgs, but to do precision QCD, we'll be able to, and comparing this Higgs to glue to Z to QQ and C to and C to QQ bar gluon, we'll be able to improve the to really separate much better the properties of gluon jets from quark jets. And then this will have many implications for, so improve quark gluon heavy quark discrimination tools, check N and low antenna functions, extract QCD I have in the backup, the QCD coupling again from all this, and of course non-peak QCD, gluon fragmentation, color reconnection, glue balls, and baryon hadronization, and so on, thanks to all these high quality data from the FCC. Of course, at the FCC-PP, we will have very extremely highly boosted jets. So it provides jets boosted to tens of TeV, and this will allow to study jet substructure to separate, for example, QCD from uncolored resonance decays, a resonance decay without color at 10 TeV, for example, with comparing all these boosted topologies, and okay, you have here a resonance at 10 TeV, and you have different Monte Carlo predictions. Also, of course, we will produce many events with more than 10 jets, and this is also relevant to looking for sphalerons and you name it. But for this, you need all again to control very well how a multi-jet, so events with more than 10, 20 jets are producing QCD. So voila. Let's go rapidly through the non-perturbative regime just for the sake of completion. Color reconnection will be able to be studied through E plus and minus going to WW to 4 jets. So the idea is to turn the W mass measurement around. So determine MW leptonically, and then also doing it hadronically. And by looking at the differences between the two decays, we'll be able to constrain if there is any color reconnection, as it was hinted at LEP or not. So that's something where again FCC will help us to improve our understanding of non-perturbative dynamics. And then there is, as I said, many things with hadronization, color string dynamics, baryon and strangeness production, final state correlations, multi-quark states, final state interactions. All these will be able to, all these hadronization studies will be studied in E plus and minus in a clean environment without any quark gluon plasma droplet, and then compared to any result in PP. So let me go to the partial summary, and then before going to my 20 last slides rapidly. So QCD at FCC and PP this is really a unique machine. We'll be able to extract with per mil accuracy alpha S via multiple observables. I focus on Z and W, but you have tau decays, jet shapes, jet rates. Of course, we'll be able to extract the parton densities with high accuracy. We'll be able to study the jet structure at very high accuracy and be able to separate quarks, light quarks, gluons, and heavy quarks. This has many implications for BSM searches. Study highly boosted jets, multi-jet final states, control of color reconnection below the percent level, high precision hadronization, and so on and so forth. So this is the combination of both machines is amazing for QCD studies. Let me go to the Higgs sector now. That's the main motivation, of course, for FCC-ee and FCC-PP. So let me show you here the cross sections. You all know we expect more than 10 to the 10 Higgs produced at FCC-PP, and more than 1 million Higgs produced at FCC-ee here. So here, this 10 to the 10 will allow us to study very rare and BSM decays, and also the self-coupling. You see it here. PP-hh has the cross sections from the LHC to the FCC-PP. The only way to measure the Higgs self-coupling is to build a machine like FCC-PP, and that's why we need the cross sections of the energy, center of mass energy of this machine. And of course, the 1.2 million Higgs will at the FCC with no background and no pileup, they will allow us to do super precise down to 2 per mil extractions of Higgs coupling. So the combination of those two machines will basically allow us to probe the Higgs sector to an impressive degree. Let me start here with FCC-ee, exploiting these 210 to the 10 these billions of Higgs. We will be able to determine rare decays with 1 to 2% precision, gamma gamma for leptons, muon, and Z plus gamma. And then, of course, we can go down to 10 to the minus 2, 10 to the minus 4 for invisible Higgs decays. Okay, so we will go beyond the standard model invisible Higgs decay through 4 neutrinos already with 1 inverse attobar. So for those things, for invisible decays and for rare decays, we need FCC-ee. For Higgs self-couplings, plural, lambda 3 and lambda 4, we need again FCC-ee, otherwise there is no cross-section. You see here how it goes from the LHC sitting here all the way up to FCC-ee. We have the only way to produce that double and triple Higgs is to go to FCC-ee. And this is early studies. Basically, a few years ago, we were preparing this. Basically, we realized at the time that the trilinear coupling will be determined with 3 to 6% accuracy. The quartic here through, is it here in this plot? I forgot it. This is not the right plot. The quartic will be mildly constrained, significance of 2 sigma, and put then limits on the lambda 3 versus lambda 4 couplings. Here, the most sensitive channel is you have those were Monte Carlo studies. This is a bit more advanced now with fast simulation. So looking at 4Bs, BB tau tau and BB gamma gamma, and then combine them. We get 3 to 5.5%, and this is the only way we have to really constrain the Higgs self-coupling. The high-lume LHC will bring a 50% precision in the self-coupling constraint, whereas this will allow us to probe this to 3 to 5%. This can be improved with FCC-ee because the Higgs trilinear is indirectly constrained through loop corrections to the Higgs Talon cross-section. So there is this process here, which is a dominant one. But you see here the Higgs coupling to itself. This is a tiny correction, but is visible thanks to the extreme 4 per mil precision on the cross-section that we'll be able to extract at the FCC-ee. So this will be able to extract set limits in the trilinear basically at the high-lume LHC level, but combined with the FCC-ee, we'll be able to go down to 2 to 3% level, also eliminating some degeneracies that are not accessible at the high-lume LHC. Now let's go to the couplings, FCC-ee. As you all know here, we use the recoil method, where basically we look at the decay of the very clean decays of the Z, in particular leptonic decays of the Z, and then we are able to extract the Higgs couplings in a model independent way. So basically, the Higgs Talon cross-section will be determined to a 4 per mil, which translates into a 2 per mil uncertainty in the Higgs to Z coupling. The total width will be also determined to 1%, combining also these accurate measurements of the cross-section with the branching ratio itself of the Higgs to Z. Combining both, you can extract the total width. And then you determine the rest of your cavas from other decays, then exploiting again this accurate cross-section and total width. So with this, we get to this, combining now FCC-ee and PP. You see here that the complementarity, the interplay is extremely good. So for electroweak bosons, of course, here EE is very good. But then when you go to rare decays, mu and gamma, then and TT, then here is where the FCC-ee wins. And as I said, the 2 to 3% combined uncertainty on the self-coupling, below 1% uncertainty on the total width, and then invisible decays and so on. So the most precise two-per-mil coupling allows one to set limits on new scalar couple physics at basically roughly in this ballpark, in this pocket formula above 6 dB. This is confirmed then with full EFT studies, but I will come back to this later on. Now at the FCC, we can also determine the Higgs mass to a few MeV precision. So through the recoil method, we're able to extract the mass of the Higgs to 5 MeV. So 8 MeV with the Z to mu mu, and then adding sig to E and adding all decays. At the end, we get to 5 MeV. And then the question we asked ourselves a couple of years ago is, can we do a threshold scan to the Higgs Talon cross-section as a function of square root of S at FCC-ee and try to determine MH as we do MW via the threshold scan at the E plus and minus going to WW threshold? And the answer is yes. The answer is that by doing a threshold scan around 217 GB around here, that's where the maximum slope of the cross-section rises. We are sensitive with 5 inverse attobarn. We are able to the Higgs mass to within 5 MeV. So combining both the threshold Higgs cross-section with the recoil mass from that I mentioned here will allow us to just adding both up. So taking the square root of 2 of the 5 MeV extractions, you will get to 3 MeV ballpark of masses. Why is this important? You will see it next. Well, first of all, for the couplings is important. For the couplings is important to know the Higgs mass, but it's important also for the electron Yukawas, you will see soon, very immediately. As I said at the beginning, the generation of the lightest fermion masses is completely untested. We don't know how the UDS, let alone the neutrinos, get their masses in the standard model, because this is their coupling, their masses are very low and their coupling to Higgs is tiny. So this is basically impossible to see at the LHC. So the question is, what FCC can do for these light fermions? First of all, the light core Yukawas, here FCC-PP can set here in a model-dependent way using global fits on Higgs decay to all jets. Using global fits in the kappa framework will allow us to set these limits. Then we can set also limits from exclusive Higgs to vector meson plus gamma decays that have a very small branching ratio and huge backgrounds, but they should be studied and they should provide some constraint, as they do already at the LHC. So for the first generation, combining all FCC machines, we'll be able to set limits of basically 200 times the standard model, 280 times for the Yukawa of the U, 130 for the times the standard model value for the D, and for the second generation for the strain 6 times. And then the charm will be measured with a precision of 1%. That's combining FCC-PP and in particular FCC-ee here. And then this is a topic I've been devoting my time in the last years, is that there is no way to measure the electron Yukawa, because Higgs to E plus A minus has a branching ratio of 10 to the minus 9. So there is no way you can see this at the LHC, because you have a huge E plus A minus Drellgen and you have a tiny cross section. So the only way is to inverse the diagram, and then you produce, instead of producing the Higgs and decay into E plus E minus, what you do is you run E plus E minus Higgs at the Higgs pole, and you look at all final states. The problem with this resonance channel production at 125.000, whatever the value is, we will note, as I said, within 3 MeV, is that the cross section is tiny first. So it's for a bright Wigner with 4 MeV width is 1.64 femtobarn. The problem is that if you add ISR, so the initial state radiation from the electron and positron beams plus a beam energy spread, the center of mass energy, the beams are not monochromatic. The beam energy has a spread. So if you combine both effects and you assume that you monochromatize the beams to 4 MeV as the Higgs width, then you get a cross section of that broadens to 0.3 attobarns. Okay. So this looks daunting, but still we tried to do it. So what we did is we studied the problem we have also, of course, is that not only you go through the scalar resonance, through these final states, you go through the Z star and gamma star, you go through the T channel. So we did a generator level study of 10 decay channels of the Higgs with all the backgrounds, which are 10 to the 4, 10 to the 5 times higher. And then we realized that the most significant channel is Higgs to glue, of course, because there is no way to produce two gluons through the Z star or gamma star. But of course, for this, you have to control the light quark mistag for a gluon to the 1%. And that's where these previous studies I was mentioning of light quark gluon separation play a role. And also the WW star with lepton plus jets. Then we found out that for 10 inverse attobar, and again, running at with a beam energy spread of 4 MeV, we have a significance of 1.3 sigma. This is this point here now in the integrated luminosity versus beam energy spread. This point here is that what we found. And now from our studies, and this allows us to set limits on the Yukawa coupling of the Higgs to 1.6 times the standard model value. But of course, when we ask our accelerator colleagues, can you monochromatize the beams to 4 MeV? And they say, yes, but you have to pay the price of a luminosity loss. And basically with 6 MeV monochromatization, you go down already to 1.5 inverse attobar instead of the 10 we assume. Actually, the studies, that's the line they gave us. Okay, so this is per interaction point if you have per year. Okay, so if we are in the worst case scenario, we run for a year with 4, and then with just one IP. We know that's not going to be the case. We will be running with 2 or 4 IPs and hopefully more than a year. But this will allow us to set already limits on the Lepton Yukawa to 2.5 times the standard model. If you wonder, this is 100 times better than high luminate C and 30 times better than FCC-hh. On top of looking on the Higgs decays to be plus and minus on top of the Drell-Yan. And if you look at PSM scale that we are probing affecting the Lepton Yukawa, this limit corresponds to being above 100 TeV for any new physics impacting the electron Yukawa. Now, just in the last 5 slides, let me go rapidly through ESM searches. Both machines are extremely complementary. So first of all, let me go through indirect BSM searches at FCC-ee. So thanks to measurements of MC, the width of the Z, asymmetries, the same for the W, for the top, alpha S, and so on. These allow us to set limits and doing a stress test in the electroweak precision observables in an EFT approach. These allow us to set limits in some operators above 50 MeV, 50 TeV. Yeah, some of them about 70 TeV, 60 TeV, some of them between 40 and most of them between 40 and 50 TeV. Okay, so you see the VSM reach of FCC-ee alone is in the 50 TeV range. If for electroweak coupled physics, if you care about Higgs scalar coupled physics, then you see these lines here. Look at the dark blue. This is the estimated uncertainties on the various couplings of the Higgs, and you see here the improvement with respect to the current situation is orders of magnitude. This will allow us to probe scalar coupled physics to basically above 6 to 7 TeV. So if there is any new physics that couples to the Higgs, we'll be able to study it up to 6 TeV. In terms of direct BSM searches, then of course the gluon and quark-quark luminosity, quark-quark luminosity goes up to 50 TeV. But if you focus on your favorite model, say supersymmetry, FCC-hh will allow you to go up to masses of 20 TeV for some objects, or depending on gluinos up to 6 TeV, depending on your favorite scenario. But this will be 5 to 10 times the standard model value. Now, there is also some direct searches accessible of BSM searches at FCC, in particular for feeble interacting particles, weakly coupled particles between 1 and 100 GeV, thanks to 10 to the 12 Qcd Coupling. For example, for action like for pseudoscalars or for heavy neutral lepton right-handed neutrinos, we'll be able to set limits 2 to 3 orders of magnitude better than anything else that can be reached. You see it here. So FCC-ee is also a direct BSM. It's a discovery machine, also in the 1 to 100 GeV range. It's not, of course, in the 50 TeV range as FCC-PP, but it is in this region for weakly interacting particles. So with this, I come to my summary. I hope I was able to convince you that a machine like the Future's Circular Collider at CERN provides unparalleled center of mass energies, 100 TeV, and luminosities 20, 30 inverse at 1 for PP, up to 150 for the Z-pole in E plus minus collisions, to address many of the fundamental open problems in particle physics today that have not been solved and will likely not be solved by the LHC. So I show you that both through high precision studies of the heaviest standard model particles at the FCC-ee or direct high mass searches at the FCC-PP allow to set direct and indirect constraints on BSN up to scales above 50 TeV. This was the case for electroweak precision observables. This is like for the scalar sector is more like 6 TeV. But if you look at the system mass for a FCC-PP, you see here that you get to 50 TeV, depending on the coupling to the partons. Plus, I show you that these machines not only allow us to get to BSM above 50 TeV, but allow us to study open issues of the standard model, like how do the lightest fermions get their masses, like the electron, the light works, how the Higgs gets its own mass, what set limits on right-handed neutrinos, on ALPS, look for their matter. And then, of course, I mentioned it in the first half of my talk, QCD. I didn't discuss it, but flavor, FCC-ee at the Z-pole with 10 to the 12, you can go for extremely precise flavor studies. That's it. Thank you for your attention.
Thank you very much, David, for a very comprehensive review across all the FCC deployment modes. I'm pretty sure there are going to be questions here. I can see Roberto, so please go ahead.
Thanks for a nice talk, David. Clearly, all these precisions that you are mentioning, they require a non-negligible experimental effort, which I'm sure with the years we are going to achieve and with the various technological improvements. I'm talking just about the experimental part. For example, the RL measurement requires an extremely accurate knowledge of the acceptance of the apparatus, which was not necessary at the lab times. It was necessary, in fact, only for one piece of the apparatus, as well the luminometer. I guess the same is for the RW, right? I've not studied the specific problem. I only studied the RL part, and I remember that it's possible, but not easy. Are there specific studies concerning the acceptance for the RW, and in general, any specific systematic effect from the point of view of the experiment that should be taken into account?
What we took is the results. We didn't do any study on systematics and detector uncertainties ourselves on the W. What we took is the values that have been proposed, as you know well, by the FCC people. So this is the type of uncertainties on the total width and RW. This is the systematics that are expected. How do we get there? This is still at the statistical uncertainties level. How do we get there is tricky. But as you know, from lab times, usually one was able to match a statistical to systematic uncertainties. And for the W, some of these quantities, of course, depend on the, if you're asking me about the accuracy on the acceptance, I don't know. It's 10 to the minus 5. I think you probably know better than me for the Z that you need to know. For the W, I have to think about it. Probably it must be the same, not the same order.
Okay, probably the
this
same
is the
order.
part of studies that we need to do in this feasibility in the next 4 or 5 years, indeed, to reach this,
Okay.
to demonstrate that we can reach this.
Okay, thanks.
There is also the problem of the theory uncertainties. This is the other problem, because when we are, it's not just the acceptance,
Yes, of course.
acceptance
Yeah.
problem. The theories
Yes.
have to provide all this also, have
Yeah.
to improve the calculations by a factor of
Yeah.
10.
That we know, yeah.
10 to the, so we need this for the all these terms for the W.
Sorry, before I move on to the next question, just jump in because it relates to what you are discussing. When you are discussing electroweak corrections, and you were showing that in some plots they do count a lot, because alpha W we know is like alpha S squared. Can I just check from a technical point of view that the full electroweak correction are including, meaning the non-factorizable correction, which can be very large at 350 GV, which were not at 90 GV, as opposed to some mock-up scheme which captures only some of the factorizable corrections?
Here we focus on the Z-pole, which is probably more under control. I don't know, the TT bar, then you have also, yes, you have to already the running of the at this level of accuracy and precision, already the running of the alpha S from 91 GB to 300 through the M top to needs to be computed beyond alpha S to the 5. So already the running is at this level. So what we did in particular, I can tell you, is that this we added. There are this we added in this study with that I did last year. What we did is where is it? The theory, yeah, right here. What we did is we did a full N3LO fit, so including mix corrections for this. Let me show it again. So for the W, these electroweak corrections and these mix corrections were known, but were not added to the.
Okay.
They were not added to the formula to start alpha S. What we did is we included them, and then that's the uncertainty that you get today. So that's the current uncertainty.
All right. Okay.
You see, it is the parametric that dominates in any case. The theory now is very small, but that's not the case at the FCC-ee anymore. Let me see where it is. At the FCC-ee, you will have these types of statistical uncertainties. You see that they are 10 times better than the theory today. Mm-hmm. So we have to, well, you guys, theories have to compute alpha S to the 5, alpha square, alpha cube, and then the mix in order to go from 0.014 to 0.0019. Right. This is the type of improvement we need.
Yeah, point taken. The next one up is Roberto Franceschini. He's telling me that he's got some problem with background noise. So Roberto, try asking the question. If not, I'll read it aloud myself from the chat.
Yes, I can try. And I was basically asking what's the change in these results. If instead of considering a 100 kilometer circular machine, I would have to consider a modern, say, 2040 version of LEP, which can run certainly at 240 GVs and lower energies with reduced luminosity, because it would be otherwise too costly in terms of wall power. But it's a tunnel that we have already, and somebody might just ask, what's the gain of getting this big tunnel if you already have one, which you can run, on which you can run a better machine than LEP.
Yes, this was called LEP3. This was proposed 5 years ago, and this was discarded by the CERN management and also by the strategy update. The problem with the LEP3 is that you don't get to this. These lumis here are because of the 100 kilometer. If you have to run on a 25 circumference, then you have a huge loss through synchrotron radiation, and then you are basically in this range here. So basically, well, Roberto Tenchini can say more because he was one of the people looking into this 5-6 years ago. But basically, you all these BSM reach, all these indirect constraints, all these accuracy in the couplings, all this gets lost because you're not dealing anymore, for example, for the Higgs with 2 per mil uncertainties on the Qcd coupling. Now you're dealing with something which is probably the Halloumi LHC range. So, and the same goes for the Z. Of course, we'll have we have much better detectors. We have more LUMI. We have, but still, okay, we'll get we will not get a Tera Z. We'll get a Giga Z machine with a Lep3 running at the Z pole. But then, of course, you have to scale all these limits. Take a look at the BSM. If you're interested in electroweak precision observable tests, take a look at you can scale the values basically here by looking at this plot. I was mentioning the Higgs, but let's take a look at the. So you see, do we have a LEP here? No, but okay, we can get to the 50 TeV range with 10 to the 12. Now you have 1,000 times less. You have to scale all this by a factor of 30.
Yeah, I suppose I get that the lower luminosity does worsen all results. The point is how much.
Yes, you have, okay, the electroweak today is here. So probably with 10 to the 9, if you just do the square root of LUMI, you will get from this down to a factor of 30 less. So you will be better than LEP, but not substantially better. But yes, but you're right. We have the tunnel. So
if I can comment,
kind of, you know, I understand the reason for putting a future 20, whatever, 60 to 90 other machine. In the meantime, yes, you have built this tunnel. It's probably 10 billions. And I mean, if it's a very big game changer, I think it needs to be stressed more. On my hand, I'm not so sure I do see it's so bleak. I mean, if I was given 100% certainty that this Lep3 or Lep240, as I like to call it, can go online at the end of ILUMI, I wouldn't dismiss it so quickly, but I understand that people have thought about it.
The problem is also an accelerator problem. We don't have the time to build the magnets, the Navier-Yonkin magnets. We need 30 years. I mean, the people building those, they need the R&D, the industrial production, and so on and so forth. So even if you, we need to wait for the FCC PP 30 years from now before we start, because we don't have today the power to build the magnets. But the tunnel can be built fast. And once you have the tunnel, because you will need it also for FCC PP, then you can put the FCC ring. And then since the tunnel, which is the main cost, will be built already, then why don't you put the FCC ring? Because again, the Lep3 will not gain much compared to the Halloumi LHC.
Yeah, no, I do get the logic of you know, reuse of the tunnel. I was just asking. I mean, in these projections, not on necessarily on this. I mean, the luminosity is reduced, fine, but sometimes yes, I really lack you know, this information in these plots where I should basically, you know, attach to each of these results. What would be the cheaper option? You know, if I had to spend this money, I want to know why I'm spending 10 billions more to build 100-kilometer tunnel, and maybe then this other machine. I say maybe then also for the reason that the reasons why you build colliders today, it's not guaranteed that it will keep being constant, and maybe at the end of whatever next machine, we will have other ideas, better ideas probably, to probe new physics. So this very long-term plan, it's nice to have, but I also accept it with some degree of skepticism. So the fact that you can reuse is a bit double-sided. So the fact that there is an option for low cost, let's say X factory,
I think it should not be dismissed. And if there is a big difference, as you're saying, in these measurements are a lot better and everything works so much better, I would stress it more, just because one day we will have to convince somebody that we cannot work with the toy we already have. The 27-kilometer tunnel is just not enough. So I think that's really a message.
Francesco, take a look at this slide, which
yes.
I don't think any of these issues, all these issues need for an energy frontier machine and a super high Lumi FCC-ee, and a super high Lumi EE collider. Anything of this you want, I mean, LEP3 instrumenting a LEP3 ring will not give you anything. I don't know, tell me one thing here in this slide that you think you can probe with LEP3.
Maybe none of them, but that's not necessarily a problem, in the sense that by the time you want to deepen your knowledge of the Higgs, and you know that it will take the next generation after the high Lumi LHC. And once that task is accomplished, maybe a little worse because you had a little less luminosity with this Lepton 3. The questions that you will have, maybe you will find other ways of probing it or other ways of building colliders. Myself, I work on muon colliders these days, and I'm very happy about the thinking that maybe could be just following the Higgs factory. And also, I should say that, yes, we definitely go around with this list of topics that are open questions at the BSM, but the vast majority of these questions are not at all guaranteed to have any answer at any collider in the range of 10 or hundreds of TeVs. So we do the shopping list, but we
I mean, the Higgs self-coupling, there is no way to do it unless you build this.
I said a very small number of these items, have a solution that requires colliders at 10 TeV. Lots of things, the origin of quark masses. There are solutions from the 10 TeV scale up to the gap scale. No collider will ever give you a definite answer. So yes, we want to probe them, fine, but there are plenty of things that we have where colliders can just scratch the surface if you want, whatever the collider it is. So what I'm saying is that we may change our attitude and we concerning these questions, and we will also never really finish the job with these questions. So if you want to use these questions to motivate 100 TeV PP machine, I keep some of my skepticism, because this is really a little wishful thinking. I'm fine with not having guaranteed discoveries. Okay, I am totally fine with that. I do not think that we need a Higgs case as we had for the LHC. But making this list and saying that you will do wonderful work about the origin of quark masses, I think it's really naive.
Okay, I think I should stop the discussion. I think the 2 points of views are very clear, but I would like to give the chance to others to ask questions. I think Roberto Tenchini, that is, also had a question.
I didn't want to go to the argument. Simply give some additional information on the LEP3 option, which has some interesting aspects. However, you have to take into account the fact that if you do what Roberto F was mentioning in the chat, that is to use exactly the same wall power, which is important because environmental consideration is very important nowadays. At that point, you already start with a limit that is 2 orders of magnitude down in luminosity, but this is optimistic, and at the Z. Then you have to, if you want to make an X factory, so go to the ZH production, you have really to fill up the tunnel with superconducting cavities, and you are going to have a low luminosity X factory, which at the end of the day will not really improve with respect to what high luminosity LHC will do for the coupling, with the exception, of course, being that in plus and minus machine, you can have an absolute measurement of the X production cross section, and you measure the total width, these sort of things. But so there is some interesting there clearly, and you don't have all the bonus of accessing also this potential of discovery that you have in the case of FCC. So I mean, and it will not be a completely cheap machine also in that case. So I mean, that is one of the reasons that at the end of the day, in order to have a longer perspective on the future and to see really discuss the future of particle physics in this century, the LEP3 option has been put down in a way.
Thank you, Roberto T, for contributing that. Did you have another questions? I thought you raised a hand before the discussion started, or maybe I'm mistaken. Okay, no. If not, maybe I'll ask a couple of questions if nobody else jumps in. So I liked a lot the part on QCD. So a couple of questions on that side. So you concentrated quite rightly on alpha S, on how you could improve alpha S. But what I'm keen to understand is that we really pinned down QCD at LEP when we were able to measure the Casimir factor, CF and CA, normalized to TR, so using 4 jet events. It's at that point that we could rule out all alternative gauge structure QCD. However, at the time, there were alternative models to the standard model like supersymmetry, which would predict like gluinos, which could effectively change CF and CA. I was wondering, are there any studies for what would be the precision that you will be able to measure the Casimir factors, which in turn would enable you to constrain models which have additional color states, which could be appearing at 250 GeV?
Yes, this is
the situation there.
Yes, this is a very good point. I myself was wondering about this, and I have an open directory on my computer dedicated to this, but I didn't start it yet. That's something I wanted to see. It's true that when I said that the QCD is a theory with just a single parameter, it's true that I'm assuming that the Casimir factors are given, but it's true that we have to measure them. So I fully agree with you. What I can say is that you have this huge number of jets that you can play with the z-pole and derive this with some much better accuracy. But yes, it's a good point. It needs to be studied.
Yeah, thank you. I'm monitoring my audience, but I don't think they have any other questions. So maybe I ask my second question. Again on QCD, so you quite rightly emphasized the fact that in a +/- machine through hadron production, you can do lots of tests of QCD that you cannot afford to do at a PP machine. In particular, the ability of separating gluon from quark jets and the flavor of quark jet is so much better in +/- machine. That's fine. I accept that. You can start reusing the old time-honored method of the jet charge. You can take the machine learning method that you've developed at the LAC and implant them into +/-, and you start learning a lot about the flavor content of jets. What is not entirely clear to me is whether there are any significant advances from the detector side. So let's leave aside the phenomenological tools. If I go to the detector, what's the expectation there? Will we get much better verticing that we have been able to get at LEP and what we're getting now at the LAC, so we can start separating much better than we've ever been able to do the displaced vertex of the C quark from the one of the B quark and so on and so forth. What are from the experimental side the improvement necessary to match all these advances from the phenomenological side? That links a little bit to the point that Roberto T made about improving the detector as well to keep up with all this physics that may come out.
Yes. No, obviously, there are lots of progress both in detector and also obviously in data analysis. I mean, machine learning was unknown at the time of LEP, and all these jet substructure techniques and soft drop and so on and so forth all were completely unknown. So to answer the question, yes, the detector will be much better. Also in terms of secondary vorticing, and we'll have also timing capabilities also. And what I want to do, just to let you know, is that I want to do something which would be the ultimate quark gluon, light quark gluon separation for this reason here. Let me go to this Lepton Decays. Since I realized that the Higgs to glue is the only way to try to probe the electron Higgs coupling, and we need to control light quarks versus gluons to 10 times better than today. what I'm trying to do is now is not just do particle flow, not just do secondary vorticing, not just do fancy algorithms. What I want to do is to plug in the PID of every single hadron, neutral and charged, into my BDT, assuming that we are able, that our detectors in 20 years from now are able to not just to detect a bunch of hadrons and do standard jet clustering, but to tell you, you have a K0, you have a charged pion, you have a photon, you have a D meson, you have a D star. So my impression is that in 20 years from now, with the detectors we are planning, we'll be able to do not just the standard jet clustering that we do now, just by particle flow or just clustering energy. We'll be able to just do our almost Monte Carlo level truth clustering of every single hadron. So if we manage to do so, then we'll be able to say a gluon produces fragments into an eta prime with a 1.5% probability. This type of questions compared to a 1 per mil, I don't know, for a U or whatever it is for a D, and so on and so forth. So this kind of details will allow us to separate quarks from gluons and to understand much better and to tune our Monte Carlo so that we are prepared for the next PP machine, where of course the jet reconstruction with pileup will not be at all that accurate. No, but I think that we will have the data samples and the detectors and the knowledge in 20 years from now to do things we cannot imagine. So my plan in the next year is to go for the ultimate light quark versus gluon rejection, looking into this. Let's assume you feed it into your BDT the PID of every single hadron, assuming that you can reconstruct them. So how well your BDT will be able to separate a gluon from a light quark. And maybe we find exclusive, of course, this depends today on the Monte Carlo, but at the time we'll have the data, we will cross-check our Monte Carlo. But if we are able to identify, for example, an exclusive decay of the gluon, which is very unlikely for a light quark, then we can determine the electron Yukawa. And that's a very funny thing to imagine. There is, we found out, okay, this is Monte Carlo dependent today, but imagine we found out that there is a specific gluon decay that is very unlikely for a final state, which is very unlikely for a UDS. Then we just go for this very specific final state. So I don't know, say E prime, eta prime, eta pi pi, I have no clue. Huh? So plus, I don't know. If we find this, then we just look for this exclusive channel in E plus E minus at the Higgs pole, and when we find it, we found the signal of the electron Yukawa. So which is very different from thinking of the way we are doing today of jet clustering. Of course, to do a D0 or a D star or a B meson decay, we need to know, as you were saying at the beginning, the secondary vertex to very high accuracy, but our detectors are already planning to do so.
Thank you very much.